Welcome everyone to our second lecture. Today we want to talk about data exploration. More specifically, we want to explore data visually, so we don't want to compute any numbers or like key quantities to judge a certain data set. What we want to do is that we want to generate pictures. And with the help of these pictures, we want to understand what is going on in these data sets. For instance, a very well-known visualization is Hans Rosling's evolution of the life expectancy of different countries with respect to their GDP per capita. So here I generated an animation which displays the evolution of the GDP, of the life expectancy or the average life expectancy with respect to the GDP. So as you can see in a picture, or more appropriately in a video, we can put a lot of information into what we see. So you don't really need to understand a lot about statistics or anything. You can just visually look at it and make your own judgments and see what is going on. And this is why visualizations are so important in data analysis, because it helps you, before you start to get into the details of data crunching or number crunching, to see what is going on. And more importantly, later on, you can use those exact visualizations you use to understand the data, to make the data available to others, and to explain your most important findings. And also, I personally like this topic because I don't know, I just like visualizations, and it's just something nice to look at, even if we don't get a lot of insights. But the hope in the end is still that we generate a lot of insights. So this is what we want to do today. And we won't deal with animations like this. So this is something, if you want, you can do on your own at the end after this lecture, because what we will do is that we will be able to generate like a slice of this animation. So for a very specific year, we could simply generate this plot. At the end of this lecture, you should be able to do it, and then doing the animation is just part of using another package which animates it for you. It's not a big deal. But so we won't go into it, because it still takes a couple of minutes, I guess, to figure out how it works. More importantly, we need to figure out how we can generate a static picture like this. And what we want to use there is the Ggplot package, which is the tidyverse package for creating figures like these. And yeah, so we will look at this data set specifically. So here I've already loaded the data. So what we need is the Gapminder package, which is where the data is coming from. We will of course need the tidyverse package or the tidyverse universe. So if we attach it, then we will also be able to use the Ggplot functions. And then I just simply saved the data into a tibble, which we just call tib. So in my variable tib, there's now the data saved, so I can access it with the variable name. All right, so as we see in here, we have a lot of information. So we can see we have 6 columns, so 6 variables in this data set, consisting of country, continent, year, life expectancy, population, and GDP per capita. And first, let's do something simple. Usually, the first thing you can create is a scatter plot, which is nothing else than a lot of points scattered in the plane. So for instance, let us just, of this data set, just take let's just filter out a very specific year, say 2007, and then we just visualize, okay, what is the connection between GDP per capita, this variable here, and life expectancies. Both variables are doubles, so as you can see, there are floating point numbers also indicated by the doubles. And the others, for instance, you can see here that the country is a factor, so it's a categorical variable. Just for information, so you know what the output of this is. So as I said, we want to look at a very specific year, so we need to filter the data. What you can do here is just use the filter function. The filter function is not a function of the ggplot package, but of the dplyr package, which is still in the tidyverse. I don't want to go into details on this function, we will later use it, but the idea of this function is very straightforward. You just take a data set, our tip, and then you say, okay, what condition do you want to use? Well, we want to get all instances where the year is 2007. So where year equals 2007. Notice that you will have to use two equal signs here because, as we have already covered in the last video, one equal sign can also mean declaration, and this is why we need to use two equal signs, just to be clear. If you forget one equal sign, then the error will remind you that you usually mean two equal signs. Alright, so the result again is a new tibble, so the data is saved in a tibble. As I said last time, tibbles are the way to store rectangular data, such as tables here. And yeah, we can save that too. And therefore we now have a tibble. Alternatively, we could have also used a pipe, since the filter function is a function from the tidyverse. It really works well with the pipe, so we could have also used something like this. This sometimes helps if we want to do more steps later on. But for now, we only need the variable. So let's just work with it. And now we want to plot, as I said, a lot of points where the x coordinate of the point is the GDP and the y coordinate is the life expectancy. And as I said, ggplot2 is the package that helps us with this, which is also the package which brings us the function ggplot. And there you can specify what data we want to plot later on. So of course we want to plot the tip 2007 we just created, and if we execute this command, nothing will happen. As you can see here, there is just a blank canvas, and this is precisely what we expect from this function call, because ggplot works in multiple layers. First off, this initial layer, this ggplot, gives us a blank canvas, and in the output itself, it now knows what data we can use later on. So what we want to do now is we want to add another layer to it. So we add a layer of geoms. So what we're doing is we're adding geometric objects. As I said, I wanted to add points, and there is a geom point that does exactly that for us. And again, I also said we want to use the GDP as x coordinates of the points and the life expectancy as y coordinates. So we need to tell geom point exactly that. And what I've just described just now, saying what visual attribute of the picture relates to what variable in the data set, is called the mapping from the variable to the aesthetics. That's just the terminology ggplot uses. So what we need to declare now is the mapping we want to use. So we declare the mapping of geom point, and this is used in conjunction with the AES functions, which stands for aesthetic. So as I said, the aesthetic is the visual attribute we want to declare from the data set. So now we can declare X and Y. So I said we want as X coordinates, we want to use GDP per capita, that was the variable name, and we want to use life expectancy as the Y coordinates. So these two columns here. And now we will always take a pair of points for each line we will generate a point by taking these two coordinates, and then we'll just throw all of them into a plane, and what we will get is an error, which is inconvenient because I mistyped it. Only the P here is written in capital letter, so I didn't find it. If I correct my mistake, this will look exactly like this. And yeah, this is again what I said we would do. We'll just plot a lot of different points into the plane here. Now we have a couple of options to change our plot. For instance, a very basic thing we could do is make all of our points blue. For whatever reasons, we could do it. Then we would say, okay, color, just make the color blue. We will tell GMPoint function that. And notice that I put the color function outside of the AES functions, because as I said, the aesthetic function tells us what variable relates to a visual aspect of the plot. Here there is no variable we use. We only say, okay, make the points blue. So we don't have anything relating to the data. So instead we can, so we shouldn't put it inside the AES function here, we just put it outside. Because what happens if we put it inside? Let's just do it to see what we would get. Then we will get something like this. So notice now that that the points are not blue. I mean, obviously you won't see, you don't have blue points here. They are more like reddish. And you have now a legend which says, well, the points are called blue, which is weird if you don't know what is actually happening. So I can explain it in a second. For now, let's just do something which gives a more useful picture. So the idea of this, as I said, relating an aesthetic to the data with this AES function is that we can use, for instance, the color aspect of the picture should relate to the data. And we can relate it to the data, for instance, to say, okay, all points of a specific that belong to a specific continent should be of the same color. So I could use the variable continent, which contains the information which point belongs to what continent. And if I do this now, then I get something which makes more sense. And then now you will see why there is a legend now, because what this does is that Ggplot now looks at the data, sees how many unique names there are in the color aesthetic we just declared, so how many unique continents there are, and for each continent it automatically assigns a color. So it may feel weird that you declare color to be something which is not a color, because obviously you don't, in continent there is no color inside. There is all the things that are in this variable are Africa, Americas, Asia, Europe, and Oceania. So this is why it may feel weird, and this is why it also may feel more intuitive to say, well, blue is the color, I will put blue there. But what you're actually doing is well, as I said, you're checking the data set for unique values, and then the respective color is assigned automatically by Ggplot, which helps because we can now, we don't have to think about which continent gets which color now. We can just let Ggplot do its thing. And what happens here now, to explain it a bit better, so that you understand why this went wrong, is that you told Ggplot to map the color to the data blue. So what you, instead of saying make the points blue, is you said you created a new column in the data set which contains only values blue, and then you said Ggplot from that make a color arrangement. And this is why you need to be careful if you want to change the color itself, but do not want to relate it to the data inside the table. Then you will need to put it outside of the aesthetic. So again, if you put it outside, then you would get exactly what you would think you would get. Okay, another thing you can do, here we related the color aesthetic to a categorical variable, so you will get, it will check, Ggplot will check, okay, how many unique values there are in the continent column, and then it will assign the colors automatically. Instead, you could also assign the color aesthetic to a continuous variable. You can even use continuous variables multiple times. For instance, you could use life expectancy again. So you can also relate the color aesthetic to the life expectancy, which will then give you a color bar here. So it will then, give you a color bar, and in this case, the darker the color, the lower the life expectancy, and vice versa. So this is basically how Ggplot works. I mean, this is the most basic idea of it. You take a data set, you tell Ggplot my data is this, and then you know what geometric object you want to plot. At this point I wanted to plot points, so my next layer will be a point layer, and then I will have to declare, okay, which variable in my data set is part of the mapping. I will do this here, and then I can assign it to different visual aspects. I can assign the X and Y coordinates, I can assign the colors, I can assign the size of the points, for instance. There are a lot of different aesthetics we can change, and if you look into the documentation here, for instance for GM then you will usually find a section aesthetics here, which tell you, okay, all of these things you can change, and the stuff that is printed in bold you actually need to declare, otherwise Ggplot will not know what to do. I mean, here it's clear, if you don't specify both X and Y values or the X and Y coordinates, there is no useful way to plot points, so you will get an error. Okay, so let's try something else. Let's try to, instead of points, let's try to plot a line. We need to plot different variables here, because if we draw a line through all of this, this will be nonsense. So instead, let's just pick a few countries and let's see how their life expectancy evolved over time. Again, we need to explore, we need to filter the data accordingly. So our table, instead of filtering with respect to year, we can filter with respect to country. So here, just filter, for instance, say if you only want to get Germany, then you use filter country is equal to Germany, remember the two equal signs, and then you will get a data set which only contains the data with respect to Germany. If you want to use more countries, you can put a logical OR function. This here is a logical OR. You can do the same, combine multiple statements with an OR. So for instance, we could now say, okay, I want to get all the data that belongs to country Germany or to Afghanistan. And now I will have a table or a data set which only contains these two countries. Alternatively, as you can see, it will be a pain to always write this down in this fashion. If we have more than two countries, we could also use the in operator, which just says, okay, check whether the country is in the following vector, or if the country is among the following collection of countries. This would give us the exact same data, but it's written differently. And of course, you can imagine that this scales better. For instance, if we want to use 5 countries, I've prepared a few, then we can just use this vector later on to filter accordingly. So we use the same code, and instead of a vector consisting of 2 countries, we can just use the vector we just created. And now I have a data set which is exactly what I'm looking for. So it contains the data of these 5 countries. And the evolution of the life expectancy I now want to plot. So what might be a good visualization for that? So a good visualization for that would be a line plot. So instead of points, we now want to draw lines. And it works exactly the same. So the first initial layer just initializes a blank canvas with respect to the data set. And now we can just use, instead of gm point, we can just use gm line. And then we have to declare the mapping again. Gm line still needs x and y coordinates because it needs to basically connect the points. So we will need to declare x is the year variable, and y is equal to the life expectancy. Now, of course, if I plot this, this will look weird. This is because in my data set, I have a mixture of different countries, and by default what gmline will do is that it will basically do a scatter plot, and instead of plotting the points, it will connect the points. And this is what we do here, what we see here. Of course, we want to draw a line for each country separately. So again, we will need to declare the color static. Because it relates to data, we will have it inside of the AES function, or have it part of the mapping. So here we relate country, color to country, and then as expected we get 5 different lines, for one for each country. Okay, so as I said, Ggplot works in layers. So theoretically, I could add another layer here. I just could, I don't know, throw in another geometric object. Here it might make sense to, instead of only having the line, we also want to have the points so that we can see, okay, what data do we actually have and what is interpolated in between. So we can add the exact same layer, but instead of the line as a line geometric object, we want to use the point geometric object. And if I do that, then I will have both. I will have a line and I will have the points. So again, ggplot stacks just the geometric objects on top of each other. And this is how you generate a plot like this. Okay. So let's go into a bit more detail about how ggplot works. More precisely, this layered grammar of graphics consists of a couple of how do I want to put it? or more or less each layer is a combination of multiple things. And these multiple things I have written in the lecture notes, but I've just copy and pasted it in here. So each layer consists of a data, a geometric object, and mapping. So this part here we have already seen. These two are still mysterious to us. We will worry about those well soon enough. But first, let me stress one thing. I just said that each layer consists of data, geometric objects, so the geom, and the mapping. Which is weird because, or might seem weird because we have only initialized the first layer with the data. So we could think, okay, only the first layer consists of data only, and the second and third layer consists of mapping and geometric object only, but not of data. But this is not actually true, because what we are missing is that actually all of the everything from the initial layer is inherited to the next layer. So instead of this here, we could have also put the data into each layer. And we would get the exact same plot. Of course, it's not ideal to copy and paste the data into each layer. So this is why, while it is true that the data is part of each and every layer, if we want to use the same data in each layer, then we might as well just put it into the first one. And the rest of the information is just inherited from the initial layer to all the other layers. And the idea works even better if we, or works even more, or more extensively, I think this is what I'm trying to say here, is that we can not only inherit the data, or the next layers can not only inherit the data, they can also inherit the mapping. So basically everything that is common in each layer can be declared in the very first initial layer. So instead of writing the mapping into each additional layer, we could also simply just declare everything in the initial layer and just add the geoms later on. And again, this will give us the exact same plot. All right. One last thing I want to say before I move on is that here I've just now put in a lot of additional information into the code. What I mean is that I have declared data is equal to and mapping is equal to. But Ggplot is in a way smart enough to detect that if an input variable is a data set like a tibble, then it's probably the data, so I don't actually need to declare data. Similarly, if I use the AES function, well, this probably relates to the mapping, so I don't need to declare this. I can just leave it out. This will actually save me some space, and it is less typing if you already know the syntax. What's more is that within the aesthetic, I could also leave out the X and the Y, because for instance, if I look at GM line, the order of the aesthetics here is also the order that is used by default. So if I just not declare the X here, I just use year, then it will automatically assume that the first variable relates to the X aesthetic probably. And the same thing with the Y. With the color, I will need to declare it. So there's nothing I can do about it. But again, here I would have saved a little bit of a little bit of space. Also, you can individualize layers. For instance, we in this layer now we have, or in the initial layer, we have everything that is common in all layers. But for instance, if I want to change the shape of my points, then I can, within the point layer, I can simply declare AES, because as we've seen for GM point, one static is the shape. So I can map shape to country. So of course the shape wouldn't make sense to change for line, so I need to put it into the individual layer. And here Ggplot will understand that the shape is only meant for the point layer, everything else remains unchanged. And here in the legend you can see now that each country is assigned a different shape of points. Okay, so that's that in this chapter, or in this video on our second lecture. I will use the long form of the code. So I will always write out data and mapping and stuff like this, because of course you're still learning it. So this is why in this video I will use the long form, so you can get used to what goes where in the code. But then for the next chapter I will then of course use the abbreviated version, because I hope by now then you're familiar with the syntax after a couple of exercises. Okay, so let's see what is going on with the statistical transformations and all the other parts of the layered grammar of graphics. We can think about it in the following way. Let's just say that, of course, the data in itself is not perfect. If you plot points like this, then of course you just plot the data that you have. But if you draw a line through all of the points, then you might say, okay, my data is exact, and then I know the evolution from one data point to the next. But and this is what I think it is, or what in data science speak you could say, I know this is the model of the data. But of course you will have errors in estimating or errors in measuring whatever it is you're measuring, for instance the life expectancy or whatever. So you would think that the real life expectancy would deviate some from these lines here. So instead of drawing a line through all the points, you could just try to find an approximation that is kind of close to the points but approximates this sort of well. For instance, a common idea is to draw a straight line through all of these points here, for instance. This will admit that there is probably an error within the points, but the straight line will probably overall be still correct. So this is why one usually does not draw a line through all of the points, but one tries to approximate it with a sort of smooth function. And in Ggplot we can do that too, of course, which is done with the stat smooth layer. So here, instead of GM line, let's now use GM smooth. I wanted to use stat smooth, whatever. So here what you can see now are a couple of things. Can I make it bigger? Yeah. I mean, I know that I can make it bigger, but if you can still see it in the video, but it seems like you can. So here you see that my line is not going through all of the points exactly. Here, for instance, you can see a deviation, but still it's close to my initial data. And what you also see is that there is a gray area around the lines, which is called confidence bands. We don't want to deal with it, so we can get rid of it if we tell Ggplot to, which we'll do in a second. And here it says that it's using the method less, which doesn't need to concern us. But the point is here, the command did exactly as what we wanted to. So let us get rid of the gray areas, and now instead of, for instance, using letting the shape of the line be whatever it wants, let's just try to make it a straight line. And ggplot lets us do it if we specify the stat smooth aesthetic a bit, or the stat smooth layer. So first of all, we don't want to have the gray areas. That can be controlled via setting SE to false. And what we also want to do instead of the method less here, which lets the line take any shape at once, we want to use a linear function instead. So what we need to say is that, well, instead of using method less, use method LM, which stands for linear model. And then you get a straight line fitted through all the points. So in machine learning speak, what we say is that if we try to find a function that approximates our data points really well, we say we're fitting a function to the data. Okay, so let's come back to the layered grammar of graphics. As I said, it also contains, each layer contains a statistical transformation. And here the statistical transformation becomes quite obvious, because as we see, we have just plotted a line now, but where is this data coming from? I mean, the line should be some points that are connected, but the points we have in our data are the points that are plotted here explicitly. So the points that are connected to form the line are not really in our data set. They come from somewhere magically. And this is the idea of a statistical transformation. What we've just plotted now was not the data itself, but a statistical transformation of the data. So instead of plotting the data immediately, ggplot, if it performs the statistical transformation, will run some computations and then use the result of that computation and plot those things. And this is actually what we've done here. This is why this layer we've added is called stat smooth, to make it more obvious that we're using a statistical transformation. And here it just understood that, okay, my x and y, let me give you the long form of it. I've copied and pasted the wrong one. So my x and y coordinates are known, and now stat smooth tries to run a statistical transformation from this information. And of course it does this for every country. And yeah, here it becomes obvious that we're running a statistical transformation, but I also said that the statistical transformation is part of every layer. And this might seem false, but in fact it's actually true, because if we, for instance, look into the documentation of GM here, then you will see that each layer contains an argument stat, and most of the time the stat is identity, which basically says take the data, don't change anything, and then plot it. And here, if we look into stat smooth, then it will say, okay, it uses, well, the stat smooth. This is what it's called to in ggplot to fit a function like this. And so as I said, we can make it obvious in our code that we're using a statistical transformation. If we write stat, but we could also, as I've by mistake done earlier, just write gm smooth. Here this will generate the same plot, because for each gm or for each stat, for each statistical transformation, there's also a corresponding gm which has a lot of defaults. So for instance, here in the gm for stat, for gm smooth, you can see that the stat is smooth by default, so it will just use the output of stat smooth. And stats and gms are interrelated. So as I said, I can in each layer you have a statistical transformation and you have a gm, so you can kind of mix it. So here we have, in this layer, we have now the GM line, as we can see, and we have the statistical transformation smooth. If we want to just use the default, that's fine, but if we want to use a different a geometric object for whatever statistical transformation we ran, then we need to use the stat variant, and we will need to declare the GM within that layer. So for instance, if I write GM point now, then instead of using the GM line, it will use the GM points now. Let me comment the other points. And then you see, okay, instead of using the GM line here, it used the GM point and plotted the transformed variables as points. So this is in the end what how these statistical transformations and GMs work together. And for a lot of statistical transformation, there's a good default, so you often don't need to change it. But what you need often, or at least in the beginning, is an overview of what GMs and what statistical transformations are there. And for that, if you're using RStudio, then you can look at help, cheat sheets, and then data visualization with Ggplot. And this will open like a cheat sheet here, which looks really messy at first. You kind of have to work with it a bit, but once you got the hang of it, then you can find a lot of information here. So for instance, let's see, where do we have GM point and GM line? So we should have it here, two variables, both are continuous. Then we could, for instance, use GM point here. And yeah, so the GM line should be hidden somewhere here. Are here line segments. In any case, there are a lot of GMs and you can try out a lot of them. We will see a couple more within the next few minutes as part of this video. But if you're unsure or you need to be reminded what GMs and statistical transformations there are, then you can look at the cheat sheet here. All right, so I kind of left out why it can still be a good idea to use a string. So for instance, when we said color is equal to blue within the aesthetic or within the mapping, then we use the string, so one single string, as a mapping for color, for instance. And I kind of left out why this could be something useful. So here, let me redeem myself and deliver what we want to do, or show you what we could do. I will just copy and paste it from the lecture notes. Basically, what we do here is we draw a scatter plot of GDP versus life expectancy, and then we run two different smoothing functions, or what we try to fit two different lines. The one is the automatic approach, where we don't change anything. We just say, well, GM smooth, run your course. And in the other fitting, we try to fit a straight line. That's where we then say, okay, method is equal to lm. And here in each layer, we declared that color should be mapped to a string here. And this helps us. Oops, I need tip 2007. This generates the following plot, because as we can see now, we have a legend now according to the strings we declared earlier. So sometimes if we have two categories you want to name manually, then this is where it can be helpful to declare the mapping yourself via a string. All right, so that's what statistical transformations are about. So let us take a look at a couple more examples. So for tip 2007, we could, for instance, generate a histogram. So we want to see, okay, what's the distribution of the life expectancy? And a useful visualization for that is a histogram. That's pretty straightforward to use, and with ggplots you just declare the data, of course. The mapping will just be then, you just have to specify the x variables or the x coordinates. So in this case we want to get the distribution of life expectancy. So you just declare that, and then you need to add a GM histogram. Even though this is a statistical transformation, I'm happy with the default, so I will just use GM histogram instead of stat histogram. And then I get exactly what I want. I get a histogram. And yeah, so a histogram is nothing else than just counting how many instances of life expectancy fall within specific widths. So here we can see that, what is that, approximately 7, in the year 2007, approximately 7 countries had a life expectancy which were just below 60. Okay, and as before, we could map a continent to color. So we could, for instance, say, okay, make fill equal to continent, or map fill to continent. Then we'll get something like this. So here, I know I said I wanted to change the color, but what I've written is the fill, because histogram, if you look into the documentation, you will see that it has the same aesthetics as GM bar, and there you will see that there are 2 aesthetics. One is color, one is fill. And if I want to change, I'll just show you what happens if I use color. It just changes basically the edges of the bars and colors them accordingly. But often what we want to use is we want to change the color of the filling of the bars. So we just have to specify the fill. And what you can see here now is that it also, first of all, there are differences, of course, in the life expectancies between continents. I think that's not a shocker. That was kind of obvious before we even started. So here you can see Africa on average has a very low life expectancy compared to, for instance, Europe, which is depicted here in blue. But what you also see is that the bars of the histogram are stacked on top of each other. And this is where the position alignment of the layered grammar of graphics comes in, because sometimes we will need to adjust the position manually. So for instance, here for this layer we would have to specify the position. There are a couple of options. You can either say identity, stack them. In this case, stacking is the default. It just stacks the bars on top of each other. You could say dodge, or you could use fill. You can play. You will be able to play around with those in the exercises. Here, just let me just demonstrate dodge, for instance. So the bars try to dodge each other, and they are plotted next to each other. So this is how you could change the position alignment of a layer, because as you can see here, each layer or each GM function contains a position argument. If you use identity, then they are just plotted well above each other, not on top of each other, but the layers are stacked here, which is bad if you have too much overlap, so you cannot see everything. There sometimes it helps to make the bars transparent, which is usually controlled via the alpha argument, so you could make them more transparent if you change it from 1, which is not transparent at all, towards 0, which means completely transparent. So changing it to 0.5 you see that the bars became transparent and that you can see more now. Okay, again, this is a statistical transformation, so you know that these counts here, so what we have on our SY, on SY coordinate here, is computed from the data. So the count you won't be able to find in the data set. And as I also said, that a histogram is something which relates to the distribution of a variable, in this case life expectancy. And in probability theory, we know that it approximates, or from probability theory, we know that it approximates the density of a variable. And here this would become more obvious if we, instead of counts, so here it counted how many times did the life expectancy fall within one bin. Instead, we would rescale the number so that it resembles something like a density. And we can do that. We just have to tell ggplot to do that for us, because same as y is as the count is a computed variable for the count, for the y aesthetic, we can also the density, which you can see in the documentation of GM histogram. Not only the count is computed, you see that in the section computed variables, but also the density. So if I want to specify, okay, as y aesthetic, instead of using the count, use the density variable, which you compute anyway. And if we want to use internally computed variables, we just have to use 2 points, followed by the variable name, so you want to use density, followed by the other variable, followed by 2 points again. And as you see here, then now density instead of count is plotted. Okay, of course, there's also a statistical transformation density. So you could also compute stat density, because it basically works the same as before as GM histogram. I will just copy and paste it from the lecture notes. Here I just used the stat density layer to visualize or estimate the density of our distribution. Okay, and what we could also do, if we also want to make it more obvious how the plot looks for each color, we can make the color be black, and then we have some edges to differentiate the different plots better. Okay, so let us go through one more quick statistical transformation. So as I said, density works basically the same as histogram, it's just a different way of looking at it. A completely different visualization of a distribution is a box plot, which summarizes the quantiles of a distribution. For instance, let us look at the distribution of life expectancy overall, so for all countries in 2007. Then we can just say, okay, we want to get the quantiles or the box plot for life expectancy. We can either decide if the box plot is plotted horizontally or vertically. This will then change depending on what we want. If we use X or Y here, I will use Y here. And then we just add a GM box plot layer. And what this is now, a box plot, is as I said, a summary of the quantiles. So basically, this straight line here gives us the range of the life expectancy. So we know that in our data set, so in 2007, we had the lowest life expectancy of 40 and the highest life expectancy of 80. the median life expectancy. So the value for which 50% of the data lies below this value and 50% lies above it is given here by this straight line, or for this bold line, which says that okay, approximately 50 or the median is, what is that, 72 years, and then the box itself contains 50% of the data. So here the upper line of the box is the 75% quantile, so the value for which 75% of the data are below this value, and the lower line of the box is the 25% quantile. So 25% of the data is below that value, so in this case, what is that, 58 years, and together the box of course forms then 50% of the data. So basically there's not a lot of information in there. Of course, a density plot contains way more detailed information about the distribution, but it is a neat summary. And what is nice about it is that because it's a really quick summary, it doesn't take up much space, so you can align more of those box plots next to each other and have a quick overview. As you saw here, for each continent I plotted a density and it became messy. I have to figure out in this area, for instance, okay, which plot belongs to what continent and how much do they overlap. In any case, it's messy. With box plots you don't have the same problem because it's a really simple summary and you can plot a lot of them just next to each other, and then you can immediately visually compare. What you need to do for that is just, for instance, map color to continent. I use the point instead of a comma. Now it works. So here I have a box plot in its own designated region, so it was really easy to just plot it next to each other. And notice that the width of the box doesn't change anything. As you saw, when we only had one box plot, it was really wide. It doesn't matter, it doesn't have any interpretation, it's just it uses all the space there is. And here, because it's the same space but 5 box plots, the boxes become narrower. In any case, I can see what's what now, and as expected, Africa has a really low life expectancy compared to Europe or Oceania. What would be even better in this plot is if the plots were aligned somehow in ascending order, and we can do it. We just have to tell Ggplot that. Let me rearrange this a bit here. What am I doing here? Alright, this is how it's properly indented. So here I know that my continents, if I look into the data sets, they are factors. This was country, here this is continent, they are factors, so they are categorical variables. And to reorder factors, there is a function factor reorder, or abbreviated FCT reorder, which reorders the continent according to a variable. And in this case, we want to use the life expectancy to reorder it. And that's basically it. And now we see that the factors in the plot were reordered, so now it is in ascending order. Of course, the legend description became quite long, but don't worry about that, we can change that later on. In fact, we will do it in the second part of this lecture, so in the second video for this lecture, with respect to plot customization. For now, let us look at the last part of the layered grammar of graphics, the coordinate system, and the faceting scheme. As we saw with histograms here, we saw that it can get really messy if we try to stack a lot of histograms on top of each other for different variables, or in this case for different continents. Of course, sometimes what we really want is a histogram for each continent. For whatever reason, we really need those right now. Then it is a good idea to simply split the data for each continent, and then for each continent generate one histogram, and then collect all of these histograms within a single window, but this single window consists of a single window for each continent. So basically you have a window of windows, and this is what we mean when we are saying, okay, we are faceting the data or the plot. So let me copy and paste this here. We simply want to put this into facets. So here we can just say, okay, we use an additional facet layer. We have the options grid, null, or wrap. If we only want to facet according to one variable, in this case continent, then it's usually a good idea to just use facet wrap because it does all the heavy lifting for us. And then we use the vars function, which simply tells facet wrap which variables we want to use as faceting variables. It's sort of like the AES function for the mapping. It's just something we have to do. And here we know, okay, we want to use continent as a faceting variable, and what we get then is a plot. So one large window containing the single continents. So there is a window for each continent, and as you see, we can still use the other aesthetics. So we can still use the fill aesthetic here in this case to map continents to color, even though we are also using it to facet. So as you see, in each facet you now also have a different color. If that is really necessary for whatever visualization you're trying to create, so a single value and in each window, and in each window a different color, if that's really necessary, you will have to judge on your own. Sometimes it helps to just leave it the same color, but in any case, faceting can help us to order our make our visualization a bit more tidy. And now, as we can see, we can compare the histograms for each continent better, and also we don't need the alpha anymore because we don't need any transparency. And for instance, I could, if I'm unhappy with the order of if I'm happy with 2 rows and 3 columns, I could also change it to 3 rows and 2 columns, and then it's ordered differently. Okay. Also, what you can do, if you look at the facet wrap documentation, you will see that the scales are fixed. And if you noticed, then the x-axis and the y-axis, they are scaled exactly the same for each window. You could change that. Could, for instance, say, okay, the x or the y-axis should be 3. So then it will give a different scale for each y-axis, but still leaves the x-axis fixed. Of course, it will depend on your visualization, what you want to have fixed and what you want to have free. In this case, it helps to have the x scale fixed, because obviously you want to compare the distribution of different continents, so it helps to have them all in the same on the same x-axis. Okay, and one last thing before we close this video is the coordinate system. As I said, that's the last part of the layered grammar of graphics, and as before, there's a really obvious default option, so this is why we never declared any coordinate system, because by default ggplot will just use the Cartesian coordinate system, because that's more or less what we're used to. But sometimes we want to look only at a very specific part of the, for instance, the x-axis. For instance, we want to zoom into our density plot here. So let's take this plot and zoom into this area, because that's the part that is messy. Or let's zoom into here and see if we make it larger, then we can maybe see a bit better what's going on there. And all we need to do is to add another coordinate layer, so a Cartesian layer, and there we can just declare the x limits and y limits, so we zoom into those parts of the x and y axis. And that's it. It's not a big deal. It accomplished what we wanted to do, but the reason why it's still worth talking about this is because things can go wrong when you're using statistical transformation as you're doing here. For instance, you could have also said, you know what, if I only want to look at life expectancies between 60 and 75, then why not simply filter my data accordingly? Of course you can do it, but the problem will be that the picture will look different here, because statistical transformation sometimes uses all data. If you compute trying to estimate a density, then it will use all available data. And if you restrict all available data only to a specific window, then the estimated density will of course only be restricted to that window, but it will also look different in that window. So this is why you cannot simply filter out the data and say, okay, now I plot just like the way I would do without this extra Cartesian layer, but this would give a different result. But what is even worse thing to try, basically it's the same idea, but it's not as obvious, is there is also an x-lim layer. You could, instead of using Cartesian, you could also say, okay, I want to zoom into x now, into the x-axis now, and I use the exact same limits here. The syntax is a bit different here. I only need to use this layer here. And you would think that it's basically the same thing as the Cartesian layer, but it is not. It's basically the same as the filter approach I just described. It throws out all the data and then runs the statistical transformation, which will of course lead to a different result. As you see, I will make this smaller here. As you see, this is obviously not the same two plots that we have here, and this is where you have to really look out for warnings. In this case, here you will get it's a warning, but it won't be an error, so the code will still run through and it will give you a picture, but you really have to be careful about what picture you will get, because as I said, it changes the whole transformation because it removed 87 observations here. And this is something you will have to be careful about when you're using xlim with transformation. Basically the safe idea is to always use Cartesian if you want to zoom into a specific region. Okay, this concludes the layered grammar of graphics. I think that's a good, or the basics of this grammar. I think that's a good place to stop the video now. And in the second part of the lecture, the video will be shorter, I hope. It should be shorter, I don't want to do it in another hour. But plot customization is something which can take a lot of work, so I kind of only want to give you the gist of it, and then you will simply have to try it out. So this is why the next video about plot customization is something you stack on top of the basic of ggplot. So it might be a good idea to, after this video, do the exercises and then come to the second video with respect to plot customization, and yeah, just get the introduction to what I want to say about plot customization, and then you can take a look at the lecture notes and see yeah, how the plot customization is described there. Okay, that's it. Then see you in the next video. Bye.